All right, everyone, welcome back. We're going to go ahead and get started. Our first presentation is Kevin Cannon. He will be presenting the Snow Badger mission concept, trenching for ice with humans and robots.
All right, is my audio working?
Yes.
Okay, go to the next slide. Okay, so over the last really kind of 10, 20 years, we've learned a tremendous amount about volatiles at the poles of the moon. So we know that there's ice exposed at the surface, likely in the subsurface as well, but it appears to be quite different than what we see on Mercury. But there's still a ton that we don't know, particularly how deep the surface ice extends, if there's pore-filling ice or ice lenses in the subsurface, what the concentrations are like on kind of less than 100-meter scales, and the texture of how the ice is arranged in the regolith. And it's my contention that we're probably not going to learn to be able to answer these questions from further orbital remote sensing. We really need to get down on the ground and do in situ science. So if we go to the next slide. So there's a lot of talk about drilling, and for example, the Viper rover is going to use drilling, and I think we will get a lot of information out of that, but we have to keep in mind that drilling provides a one-dimensional piece of information from a single location. Now, you could say, well, we'll drill a whole bunch of holes and correlate between them, but this quote here, right from the Lunar Source book, it has not proved possible to correlate different stratigraphic layers sampled by coring over any distance on the moon, okay? So if we go to the next slide, what we can do instead of drilling, is to dig a trench. So a trench provides a complete three-dimensional picture of volatiles in the subsurface, and the strata in the walls remain intact, so they can be imaged by some of the instruments that folks have talked about this afternoon. You can drive miniature rovers into the trenches. Astronauts could walk into them. But the question is, how could we effectively dig trenches, particularly in the polar regions, in the cold traps, where we've heard that astronauts will not be able to spend a lot of time? So if we go to the next slide. So the answer that we're proposing is to use the RASSOR robot. This is a very advanced autonomous excavation rover that's been developed by the SwampWorks group at Kennedy Space Center, led by Rob Mueller. RASSOR has these counter-rotating bucket wheels that cancel out the reaction force and allow it to dig in low-gravity environments. It's able to dig over 1 meter deep slot trenches autonomously, and it has a whole bunch of really incredible capabilities. For example, in the lower left, you can see how it's able to shift its bucket wheels forward and change the center of gravity so that it can drive up slopes greater than 30 degrees. And I would encourage you to go on YouTube and look up some of the videos of this platform. Go to the next slide. So the concept of operations, this could either be launched as a standalone mission delivered by the CLIPS task order to do its own analysis. But I think the more exciting thing is what's described on the right here, is using this to support human exploration. And the idea here is that once we know the landing site for Artemis 3, one or more RASSORs could either be pre-deployed to that landing site via a CLIPS task order, or it could be part of the human landing system itself. And then these rovers would go out and dig trenches, including in either small cold traps or at the edge of a larger cold trap. And then when the astronauts go out on EVA, they have trenches available that have already been pre-dug for them. And when they're out there exploring, the RASSORs can come back, recharge their batteries, and you can repeat that cycle over again. Next slide. So these are some of the requirements here. The target mass is to get this down to 50 kilograms. It's a few kilograms over right now. We have the dimensions there. It runs off of a lithium battery. And we have an estimate there for what it would take to get this from TRL-4, where it's at now, up to flight readiness. And then we think this would pair really nicely with an instrument like USIS, which has already been described. That's a hyperspectral imaging system that could be used to analyze the walls of these trenches. So that's what I've got, and I'd be happy to answer questions in the discussion period.
Great, thank you very much. Up next, we have David Kring, who'll be presenting conducting subsurface surveys with a Crew Rover to address both scientific and ISRU objectives.
Christina, we can go to the next slide. So this is a map of calculated stability of both water ice and dry ice at 2 locations near the South Pole. One you can see is near Der Garlock and Shackleton Crater, and the other is near Amundsen Crater. And you can see that the model distributions are vastly different. We're going to need, as we move forward with our exploration program, to conduct subsurface surveys to determine if these model calculations are correct or to what extent they're correct, and to provide ground truth for orbital measurements. An ideal asset for such surveys are the crew rovers, which will be available for long periods of time between crew landings. So I want to be talking about 2 instruments that can be put on the crew rovers that the crew themselves can use, but can also be used for the long durations in between those crew landing intervals. Such rovers will be able to traverse much larger regions than smaller robotic rovers, these instruments for subsurface surveys can be used by crew as part of their IVA and provide guidance for their EVA. Next slide, please. We actually have experience with the 2 instruments that we're suggesting be common to these rovers. One is a ground penetrating radar unit. This unit was installed on the Lunar Electric Rover, which is a terrestrial prototype for a lunar small pressurized rover. You can see there it was mounted beneath the aft deck. It was completely out of the way and worked continuously during a 14-day long lunar mission simulation. These types of rovers provide greater mobility in larger exploration zones than walking EVAs, which is a Mars forward capability. The rovers also enhance crew safety, enhance crew productivity substantially, and there are NASA documents that say as much. And they provide a platform for teleoperational surveys, which I've said once before. Next slide. Here's an example of how it might work between crew landings. So we might have a crew landing at the Shackleton Crater. Well, we are. And it's in the ISIG design reference mission that there will be another crew landing at the Schrodinger Basin. In that design reference mission, 2 small pressurized rovers are tele-robotically driven from one landing site to the next landing site where crew then land and utilize them. We've demonstrated that the rovers can get between those 2 points in far less than the year between crewed missions. And so we have suggested that they go on a diverted course over to the Amundsen crater and do a subsurface survey of potential water ice and dry ice deposits to better assess the ISRU potential, and importantly, as they go from the warmer portions of this basin floor to the colder portions of the basin floor, develop the data needed to assess transport and depositional processes, and that will greatly enhance some of the science issues involved. Next slide. So here, in addition to the ground penetrating radar, we suggest that a neutron spectrometer system complement that. As I said before, the ground penetrating radar has been tested on a Crew SPR LER. The neutron spectrometer system has been tested in robotic rovers in a variety of places here on Earth. The GPR technique has been demonstrated on the Moon by the U-2 rover. The neutron spectrometer system has been selected for Viper. Both of these are low mass, low power, and low data rate instruments. And they complement each other in a very nice way. GPR detects ice at depths greater than 1 meter, potentially tens of meters deep, whereas the NSS detects hydrogen within 1 meter of the surface. The GPR can be utilized anywhere on the Moon, although the NSS is going to be ideal for polar operations. And there are some additional details in the 2-page abstract that were submitted with the meeting if you have additional questions. The thing I will leave you with next slide, is that these 2 instruments could potentially be standard equipment and outfitted on absolutely every rover that we put on the lunar surface. Thank you.
Excellent. Thank you very much. Up next, we have Seiichi Nagihara for Astronaut-Deployed Heat Flow Probe for measurements in Lunar South-Pole Region.
Hello, do you hear me okay?
Yes.
Okay, great. Okay. Good afternoon. So the picture you're looking at is the shot from Apollo 15 when David Scott is installing the second of the heat probes at the Apollo 15 site. Go to the next slide, please. Okay. So the heat flow measurements was considered to be a high science priority even during the Apollo time. So that's why it was originally planned for heat flow measurement was planned for like 4 of the Apollo missions. Then the first one was going to be Apollo 13, but of course that didn't work. So we ended up only 2 successful measurements from Apollo 15 and 17. Then so if you look at the map on the left, so then when you look at the when you try to measure heat flow, so basically we can measure the heat that comes out of the surface of the moon, right? Then actually, so the flow we capture there is actually comes from 2 major sources. One is the deep interior of the moon that comes out of the mantle, and the other source is the heat that is being produced within the crust by radiogenic decay of uranium, thorium, and potassium. So these so-called heat-producing elements are disproportionately highly concentrated in the crust. Then also even within the crust, they're more unevenly distributed, as most of you know. So that's why the so-called PKT, is considered to have a very much higher concentration of these heat-producing elements than the rest may not. But we only know from these gamma ray spectrometer measurements from the Kaguya and the lunar prospector. So that's why we have only know these things only for the surface. So we don't really know how vertically these heat-producing elements are distributed either. So that's why. So even though we have 2 measurements from the Apollo, so the SCHEM report and the latest decadal survey, and also the latest study by the leak, they all say we need a lot more measurements than just 2 data points. So we need to be able to characterize the heat flow from different terrains. Then also we want to see if there's a correlation between the heat production within the crust and its thickness, right? Then so now we kind of think about how we can help this opportunity of the Artemis human landing missions for acquiring more heat flow data. So then if you look at the map on the right, so that's the topo map of the Lunar South Pole. Then so the elevation is color coded, but you can also see these black contour lines. So those are the estimates of crustal thickness from the Grail mission in kilometers. So that's if you look at the circle of the 85 degrees south. So within that circle alone, so you have a place where the crust is thicker than 50 kilometers. And then there's also a place the crust is thinner than 30 kilometers. Then if you expand a little bit further out, you can even find places the crust is even thinner than 20 kilometers. So that's why if we can send astronauts at different locations in the Lunar SouthPolar regions, then if they can drive around, then they may be able to actually collect more heat flow data points from places with variable crustal thickness. Then that will really take us really, very far in sort of constraining the heat production within the crust. Then also for the South Pole, if you can also make measurements in dark places, then we could also use that data to infer the stability of the volatiles in the subsurface. So that's why that's another reason we are interested in collecting more heat flow measurements from these South Polar regions. Next slide, please. So here, this is how the Apollo astronauts did, right? So if you remember from Chris Zacny's talk about an hour ago, so he talked about the Apollo lunar surface drill quite a bit. So the astronauts drilled a hole. Then actually they used the auger for the drill as the casing of the hole. Then here we go. So they slid these sensors down into the hole. Then the heat flow was obtained as a thermal gradient times thermal conductivity. So you make different temperature and thermal conductivity measurements and different depths, then you get the heat flow, right? We could pretty much duplicate what the Apollo astronauts did, but there are some room for improvements. Please go to the next slide. Right. So the one thing we may want to do is we should make the measurements in the open hole. So one of the interesting findings from Apollo 17 is that if you drill a hole, then take the augers out, the actually hole does not collapse, right? So that's why actually we could install.
And we're going to need to wrap up.
Yes, yeah. So then we can get a much better coupling between the sensors and the regolith. So that will improve the data quality. Then also, you know, I'm sure that in the lots of audience in the audience, there are a lot of people who want to have the cone samples taken back from the moon. So that's why we can actually combine the heat flow measurements with the coring operation, right? To use the time of the astronauts more efficiently. Then also we can make some improvement in the way we deploy the probe. So the picture on the right is one of the designs Chris Zacny's group came up with in about 10 years ago about these. The sensor is more compact and then has much less thermal mass. So that's why they equilibrate to the surrounding regolith a lot quicker than the Apollo probe did. So we could use something like that to collect more data more efficiently with help from the astronauts. Okay, thank you very much.
Great, thank you very much. Up next, we have Kieran Carroll presenting lunar surface gravimetry vis-a-vis Artemis.
Okay, and is my mic on? Can you hear me?
Yes.
Oh, great. Thank you. Okay, my topic's gravimetry science and possible opportunities for conducting that during Artemis missions. Next slide, please. Just briefly, for those of you who may not be familiar with Canadensis, we're a small space engineering company based near Toronto in Canada. And with support from the Canadian Space Agency, we're developing several space exploration technologies and products, including small lunar rovers and science instruments. And one of those instruments is a lunar compatible gravimeter, which I'll describe further shortly. Next slide, please. As many of you undoubtedly know, gravimetry is one of the standard geophysical techniques used for exploration for natural resources on Earth. It involves measuring the variation of the strength of the gravity signal across some survey area. You make measurements at the surface. The gravity highs and lows reflect density variations of subsurface rocks, which can help you determine their composition and structure. This is one of the very few techniques that can tell you anything about what lies below the lunar surface. Next slide, please. The technique has been used once before on the moon during Apollo 17, where astronauts Cernan and Schmidt conducted an exploration traverse across the 10-kilometer wide Taurus Littrow Valley, making many observations, including 9 gravity measurements. And these were interpreted to determine the thickness of the basalt slab underlying that valley, which in turn cast light on the mare-forming volcanic processes in that part of the moon. Now, the Traverse gravimeter instrument that was developed for use on Apollo 17 is long out of production and obsolete, but next slide, please. Canadensis is developing a modern space gravimeter instrument that's much smaller and has a much lower mass than the Apollo 17 instrument, and there's some numbers there, about 2 kilograms and about 2 U in size, 10 by 10 by 20 centimeters, as well as having about 10 times better expected accuracy than the Traverse gravimeter had. Vega is small enough to be carried on even very small lunar rovers, including the ones that Canadensis is developing. This has been under development for several years and is now at TRL-5. It's about a year and a half away from being able to fly. I'd say we should be able to support missions flying to the moon in 2022. Next slide, please. There are many interesting science investigations that can be carried out using this instrument on the moon, and with a team of about 20 international lunar geoscientists, we've taken a look at several of those, including the ones shown on this slide. For example, a Vega instrument on one or more static landers can measure the change in the moon's shape due to Earth tidal forcing, helping to determine the moon's deep mantle structure. If I had more time, I could go into considerable depth on that, but just moving on. Vega instruments carried on rovers can also survey around interesting features such as pit craters and lunar swirls, looking for signs of such things as lava tubes and high iron content ore bodies associated with those features. Next slide, please. Here are some ideas as to how those sorts of investigations could fit into the framework of Artemis missions. For example, the GLIMPS lunar tidal tomography investigation could be carried out by placing Vega instruments on one or more Artemis robotic or crewed landers, with data from all of them being taken and combined post facto to model the moon's deep interior structure. Vega instruments could be placed on lunar rover elements of Artemis missions, just as they were on the Apollo 17 lunar rover, either bolted to the rover or dismounted from the rover and put on the ground by crew. Artemis is largely about finding and exploring lunar ice deposits, and gravimetry could help with that, as I'll talk about in a couple of slides further. And finally, longer-term gravimetry surveying could help with the search for lunar caves, which could be ideal locations for long-term crewed lunar bases for avoiding hazards like extreme temperatures, micrometeoroids, and ionizing radiation. Next slide, please. So as far as the lunar ice is concerned, gravimetry can help indirectly and directly. The indirect means is you can do gravimetry surveying in and around PSRs in order to collect data that helps understand the subsurface structure and composition of the rock in and around the PSR. An important part of exploring PSRs is understanding the processes governing transport of volatiles, and that'll be partly controlled by those geological structures. That gravimetry data can help geologists develop models that can lead to predictions of ice deposit grade and depth. More directly, it's conceivable, it's possible, depending on the thickness of ice deposits and their character, that lunar ice may produce either gravity highs or lows when you drive over it, depending on the nature of how the ice is deposited. Slabs of ice will be less dense than the surrounding rock and produce gravity lows, whereas ice that's filling voids between regolith grains will produce gravity highs as they displace vacuum-filled voids, as it were. So gravimetry surveying could help determine the form of subsurface ice deposits and constrain their extent in depth.
Okay, and we need to wrap it up.
Yep, I'll finish with two quick slides just with cartoons of what those sorts of surveys could look like. Here's a drawing of a traverse across an ice slab, for example, just to illustrate what's involved. And with our instrument, we think we would be able to detect slab ice that is as thick as a few meters. And the final slide, moving on to the final slide, please. In this other case, if we're driving across regolith in which ice has infiltrated voids between regolith grains, then you get a gravity high when you drive above it. And there, the density contrast isn't as large, but we think we could see deposits as deep as perhaps 10 meters or that order. And with that, I'm done. Thank you very much.
Thank you. All right, our final talk for this block is Jacob Richardson presenting magnetic surveys to probe the lunar subsurface.
Hi, thanks. Yeah, before I get started, talking more about potential fields, but this time in a magnetic sense, I'd like to just thank my co-authors really quickly who gave a lot of really good thoughts into the content that I'll share today. And I put the big takeaway message today here in this gray box, which is just that magnetic surveys have been an important element of geophysical exploration on Earth, just like gravity, and that they'll also continue to be an important part of lunar surface exploration, going back to our heritage in the Apollo missions when we had portable magnetometers as well. So we can go to the next slide there. Yeah, so just a quick background on lunar magnetism. We know that when iron-rich igneous rocks cool down beyond a Curie temperature in the presence of a strong magnetic field, that things like lava flows and impact melts will retain a remnant magnetism that we can then measure on the surface, even after that dynamo has gone. So after there's no magnetic field left on the lunar surface. And when we brought samples back from the Apollo mission sites, we found out that indeed there were periods of time when the lunar magnetic field was as strong or stronger than Earth's present day magnetic field. And when we were at the Apollo astronaut sites, when we were at the Apollo mission sites with magnetometers, we saw variations that were local in the magnetic field of tens to hundreds of nanotesla that suggest that there's buried magnetized bodies beneath the surface at each of these sites. So when we look at the magnetic field of the moon today with orbital data, we see that there are a lot of places on the surface of the moon, including the South Pole, that have magnetic fields that would be detectable by today's magnetometers. But the resolution, the spatial resolution from orbit just isn't there to see field size features of interest, things like small, perhaps lava tubes in the future. So if we go to the next slide, we can look at some of the things that we might see if we took a magnetometer to the surface of the moon and had it traverse over space. Here, our team has sort of mapped out a couple of examples. With the top right example, we have a picture of the magnetic anomaly that you would see from maybe a small buried meteorite. And below that, we have a couple of examples of the same buried lava flow that has the same remnant magnetic intensity as we saw from a sample from Apollo 17, buried, at a similar depth to what we saw with Apollo 17 seismic data. So if we were able to basically walk from the left side of that graph to the right side of that graph, we would end up seeing a magnetic anomaly and potentially detecting that buried lava flow or potentially that buried meteorite in the subsurface. So if we saw features like this or anomalies like this, that could help us really quickly address some of these big science questions on the left. And those could feed into in situ resource utilization, like are there ore bodies in the accessible subsurface? Are there any lava tubes in the area? Probably not the South Pole, but in future Artemis missions when we go away from those. And perhaps, if we're thinking of where is the porosity at depth and where does it end, once you see a coherent block of bedrock that's magnetized, that might be your lower limit in a certain area. So we can move to the next slide. So if we do take one of these magnetic surveys to the moon, what would it look like? On Earth, this is generally done by hosting a magnetometer at the top of a boom. Here is illustrated by Renee holding a magnetometer on her back, and co-authors Ernie and Nick sort of helping her out with that. And the boom is important because it gets the magnetometer away from anthropogenic magnetic noise from electronics. In orbit, we get rid of that by suspending by tacking the magnetometers on the ends of the solar panels. And at Artemis, we could accomplish this in a lot of different ways, either with the Apollo-style tripod mount, with a handheld wand, perhaps a Gandalf wand, or even something more creative, like you see with this straw astronaut here, maybe an EVA suit mount in the future. And if we go to the next slide, my final slide, this sort of shows that the concepts of operations for any magnetic survey can really scale if we want to see some of these features, instead of just knowing the magnetic environment of the landing site, but actually discerning specific features, we'll need to at least traverse the magnetometer and collect continuous data, either as a line along a traverse or even more in a more complicated grid pattern if we want to see something like the bottom right that would give us something specific like a lunar lava tube. And the platform complexity can also scale, is the last thing I'll say. But getting real-time data or being able to integrate with some of these mobile assets would really increase the bang for the buck for some of this. So thanks.
Great, thank you very much. All right, so we are now moving into our discussion period. If you have questions for any of the speakers, feel free to go ahead and put those into the Q&A block. Our first question we have is for Kevin, and the question is, how do you know that the hot razor won't mess up the natural stratigraphy simply by digging a trench?
I don't, but they're called volatiles for a reason, right? If you disturb them or even look at them funny, you're going to lose some fraction of the volatiles. I don't think just offhand that you would completely sublimate, the entire inventory of volatiles in a trench by digging it, but that's something that we could do experiments on in the lab in a regular bin to test out.
Great, thank you. The next question is for David Kring. How small of a ground penetrating radar is still useful for 10-meter detection depth?
Well, that would require an optimization of the instrument, but this is an instrument that, as I pointed out before, has been installed on the Lunar Electric Rover, and so there it has had a dimension of about 1.5 meters by about 1/4 meter, but it also can be sized to fit on a meter-cubed rover such as Viper.
Great, thank you very much. Are there any additional questions? All right, seeing none, just a reminder to all the presenters, thank you for those who've already gone. Appreciate you sticking to the strict 5-minute time limit. We do have a lot of presentations today. I will be providing that ding noise when you have approximately 30 seconds left to give you a heads up for wrapping up for the next speaker. All right,